Hello, welcome to lecture. I did not expect, I'm wearing a mask. I didn't expect that we would be back here where our lectures are on YouTube again. But thank you, cold weather. You have, it's like COVID just with the earth. So this is just our weekly lecture, nothing fancy. We hadn't planned on doing any design problems today in class anyways, so this isn't something that isn't easy to accommodate with an online session. So thankfully, we didn't have a whole lot planned today. So that's nice. Now, what I will say is this. Last week, my dad's car alternator just went out because of the cold. Fried a bunch of his electronics. Cold weather is, for me, it's like I can take it, but cars can't, and most people can't. So if it's just too much, just send me an email. I try to be very accommodating. I know how hard it is to brave the elements sometimes when your body just isn't made for it. My body is made for cold. My body is not made for heat. So for me, the opposite is true. If it was 110 degrees, this would be like a no. I'm going to be recording this from a freezer somewhere. Anyways, this will be a fairly quick lecture. A lot of this material is from the textbook, but it's supposed to be in addition to what the textbook provides. My goal here is to provide you with a greater knowledge of the types of components that we're dealing with. So what the reading was on for today was on processors, and specifically types of processors. Okay, when you're dealing with a processor, well, first of all, what is a processor? A processor is effectively a collection of NAND gates. That's how most silicon chips are wired. You can wire a NAND gate on the molecular level. So it's one of the benefits there. For our purposes, the way that we consider a processor is a processor that inputs and outputs information. For those of you who took 350 with me last semester, if you input and you output information, you are processing in the middle. That's what we talked about. Well, a processor does so for an electronic system. It inputs information, uses mathematical operations, uses logical operations to process it, and then outputs information from there. So it's just a nice, easy flow from one end to another, where you have a processor, and then your input is information, and your output is also information. Okay, processors don't output voltages, they output info. That info happens to be in the form of voltages, but that's all it does, is it sends signals, okay? So when you're looking at processors, now all of a sudden it's very important. How do they communicate? What ways do they communicate? What are they communicating? How fast are they communicating? What are the clock speed that it's communicating on, et cetera, et cetera. So you get to this point where it's like, wow, processors can be really, really involved. Because they're just one piece of many. in this system. Where are you getting the input from? This input may be coming from sensors. This input may be coming from the user. This input may be coming from a different processor. Okay. Now, I mentioned the clock. The clock is an external component. Usually, some processors have internal clocks. That's a different story. They have an oscillator built into them. Why? Because they don't need an external clock system. It does make communication a little different, but it is what it is. So this processor will, in the presence of a clock, be processing the input information, doing logical operations with it, and outputting useful information. Okay, so inputs here, maybe other processors, sensors, sometimes can be just memory, sometimes it's direct user interaction, sometimes it's pre-built circuitry connections. Where some of the output of this same processor gets routed back through and fed back into the input. Processors are remarkably dumb. If we're going to be honest, they only do exactly what you tell them to, and even then, they don't always do that right. So, some of the inputs to your processor are going to be constant voltages. There are going to be switches. There are going to be grounds. There are going to be highs and lows. As you saw with your circuit that you built last week, if you followed the truth table, there are in your integrated chip, some of them you just had to force high and low in order to push a button and make it toggle. Well, that's how a processor works. Sometimes that's what you have to do. You connect some to voltage, you connect some to ground. And how you switch those will actually change the functionality of the switch itself. So you will have some pre-built circuitry in there. It's why a lot of processors are either wired directly to a chip. Like what they'll do is they'll put it on there, and it's a solder compound that's on this printed circuit board, and you put it in an oven and the solder compound melts and it sticks the component to it. Allows for a really nice connection. That's how a lot of circuit boards are made. That's one way to do it, but it's a really intensive process. So okay, on the other side, output is also information. Now this can be just like sensors are an input-output. This can be a voltage signal that gets sent to something where it's amplified, and that actually has a power associated with it. This can be component commands. Meaning, like, let's say as a result of this processor, you want a motor to turn on. This would go into a relay, which would then go and power a motor. Okay, so it could be a direct component command that it's giving. Output can be information that goes to other processors or integrated chips. Okay. Sometimes, like, what we're hoping to do this week is actually have the inputs and outputs be to other chips, where you're taking Raspberry Pi and using the microcontroller part, and you're actually feeding information that way. But again, it's just information. Sometimes this goes to memory. Oh, memory. Sometimes this goes to a display. Sometimes this just goes to components that provide a visual display, like LED lights, that kind of a thing. So a lot of different types of information that can be output or input into a processor. But at the end of the day, all this is it's just a control system. There's an input, there's processing done to the input, and there's output. Okay? So if we're going to take this knowledge now and say, well, when we're looking at processors, in order to really understand processors, there are 3 types of processors that the book gives you. And I need to make sure that I'm using the correct lingo here. Okay. Okay. The 3 types are a general purpose processor, which is a GPP. It's a single-use processor. They decided not to use SUP as an acronym here, and it kind of makes me sad. It's like, hey, I was just using some SUPs. SUP. Okay, and then there is the last one, which is a specific. They call it a specific usage or specific purpose processor. /SPP, or application specific, instructional processor. Or an ASIP. Which is, I mean, look, they got SPP, you got ASIP, you got GPP, but you don't have SUP. Like, what? It would have been the coolest one out of all of them, but no. I'm telling you, the man is out of control. Dang it, man. Okay, so the thing with these is that you have encountered all 3 of these different types of processors multiple times in everything that you do. Okay? You go look anywhere that has some kind of an integrated circuit in it, it has one of these 3. Okay? So the characteristics of these, we're going to go ahead and go into that. So for the general purpose processor, the idea behind a general purpose processor is that it's got to be reprogrammable. Okay? This is something where it issues commands, it deals with commands, but it's something that is able to be programmed to do whatever it is. It's put out there, and it doesn't have any specific use, doesn't have any specific purpose. It just handles inputs, it does a set function, and then it spits out outputs. Okay, so maybe not necessarily reprogrammable, but it's definitely, it has to be programmed. It's programmable. Okay. A lot of them anymore are reprogrammable, just because you can rewrite it. A lot of the microprocessors, I gave you an assignment in this class to look at microprocessors on, I think it was Mouser's website. A lot of them are general purpose processors. They're the kinds of things where if you know a little bit of assembly, you can type a code, plug it into it, feed it the series commands of what it has to do, and you can make them work that way. Sometimes these come with very simple operating systems, but the general purpose, it's much more it's much more more application oriented, where it's just kind of there for anybody to use. So when I'm trying to make sure that, yeah, it's got to be able to handle a lot of different types of math, but at the end of the day, I mean, it's just fundamental programming. You can consider a Raspberry Pi to be a GPP, because the idea is that you can go in and you can use that information to really, I mean, you can reprogram it to make it do whatever you want. It's one of those types of features where you have an idea, you program it, it spits it out, there you go, Raspberry Pi. Okay, Arduino is very much the same way. I could sit here and list 10,000 different types of microcontrollers, but really there's, I mean, microcontrollers themselves have to be programmed by the end user. They aren't specific, like, ooh, this Raspberry Pi is just for motors. Like, no, it's not. It's for anything, but we can make it work with motors. Or you can make it work with a home security system, or you can make it work with image processing software, or you can make it work with Blender. My nephew's been playing with Blender on his Raspberry Pi, and it's kind of funny. But you can make it do a whole lot of just about anything, because it's programmable. It's intended for that way. Now, GPPs, the benefits to a GPP is that it is extremely flexible. Okay, you don't like how it works when you put it out there, you get in there and you change the code, and now it works better. Yay! Okay, so it's extremely flexible, infinitely configurable. Again, you can use the same exact processor in multiple different projects. This isn't something where, you know, you take a Raspberry Pi and it only works for, this one's for motors. It's not going to do image processing. You can take that same processor, have it do image processing, and use the image processing to power the motors. It's kind of cool, because that means if you know where somebody's face is and you have a camera mounted on some kind of a 3-motor axis, you can rotate that camera to look at somebody's face. It's kind of creepy, but it's using image processing, and it's combining image processing with motor movements. It's combining, you can combine any amount of things. You can combine thermal sensing with control of HVAC systems, or you can combine thermal sensing with reporting, where you can actually make a Raspberry Pi call using a cellular chip. It's kind of interesting, but you can do anything you want to do in any electronic circuit. You can do with a GPP, and that's kind of the beauty of it. That's one of the reasons why GPPs are so great. But there are some drawbacks. Okay, if you're using a GPP for anything, the issue is that you can do, imagine you could do absolutely anything you wanted to. In reality, you can. You wanted to do absolutely anything. You learn how to crochet, you learn how to fight bulls, you learn how to hunt, you learn how to build rockets, you learn how to be an Olympic swimmer, you learn how to, you know, do all of these things. You fill your entire life with all of the you can do anything. Okay, the big issue that you run into is you don't have enough time in your life to devote to any one single topic. Well, that's kind of the way that this is. You can do anything with them, but the problem is they don't really do any one thing well. And I'm going to hear not the most optimized performance. Okay, you may have that brand new 8 GB Raspberry Pi, which I do, but it doesn't matter how many gigs of RAM it has, it's not going to be the most optimized performance because you're still running at a fixed clock speed. That clock speed has to go through an operating system to get to the program, which Python is kind of, I've heard it considered a wrapper for C++ because a lot of the functions are written in C++. So Python has to access your C++. By the time you get to Python, you may be able to execute a line of code every millisecond, whereas your clocking speed could be in the gigahertz. It's just such a high-level language. So it's not the most optimized performance. What that means is if you're looking for speedy applications, this probably isn't it. If you're looking for reduced power consumption, you're probably not looking here. In fact, you're definitely not looking here. GPPs are great for doing anything. And they're really good at prototyping. I was going to say that too. Really good for prototyping. But they're not intended for final products. And why do I say that? It's because it's not optimized. When you hand something a product, you don't want it to be like, hey, it's a Raspberry Pi. No, 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 no. You want to hand them something that says, hey, this is a very streamlined system. This is a system that uses minimal power. It's a system that operates at the maximum speed, that kind of a thing. If you were to be designing, as we go through this semester and we design IoT devices, if you're designing an IoT device and your IoT device requires you to program it in Python and requires you to have extensive, 300 lines of code in a Python program, your IoT device itself is going to have a lot of power consumption, and it's probably going to violate the principles of IoT. Similarly, if your IoT device is using a Raspberry Pi, it's probably not going to operate very quickly. Your clocking speed is going to have to be in the at least megahertz to gigahertz just so that you can get a process to happen every couple seconds. If you're looking for an update every minute, which is possible, you could lower your processing, your clocking speed, which would lower your power consumption significantly, but there's still a more optimized solution out there. GPP is great for prototyping, but it's not used for final products, just in general. Now, there are products that violate that principle. Okay, as you go to build a system, there are some people who sell Raspberry Pis or Arduinos built into systems. And sometimes they turn around and say, hey, if you want to reprogram it yourself, you can, because you can. You can reprogram just about anything. Raspberry Pis and Arduinos, well, more Raspberry Pis than Arduinos, are known to failure. Your SD cards will fail. Your board may fry because it's not always the most beautiful of connections, but oftentimes it's the SD card failing. And that's an issue. But that's part of what makes a GPP what it is. They're easy to use, they're relatively cheap, but they're just not the most optimized. There are better solutions out there to do whatever they try to do if you sit down and design the circuit. So on the other end of it, you have the single-use processors. Okay, single-use processors, which I am going to go ahead and I'm shorten that to SUP. Single-use processors are designed for one specific task. Okay, and they do that one thing well. One task. And they do it. They're usually, in fact, almost entirely not reprogrammable. Okay, What that means is once it's been programmed, it's done. You can't change it. It's built, it's hardwired into the circuitry that it's connected to. That you do it once and it does one function. Okay. A lot of processors that go with like audio equipment, you may have a processor that goes into an amplifier. They're intended for one thing. You can't turn around and make it do video processing too. You can't change what that processor does to make it do something else. It can only do audio processing. Okay, you get a sound chip. The integrated chips that we were dealing with were processors in a very low end of the sense, but you know, flip-flop is a processor. Takes input. You cannot reprogram it. It's hardwired connections. Outputs what it does. Okay. Okay, and it can do more than one task. Now, well, we look at that and we say, well, you know, with a GPP you can do just about anything. Then with an SUP, you can't do a whole lot. You do one thing. Why would you do this over that? Well, and here's where things come into play. This is cheaper by far. And go look at the prices of the microcontrollers that you were looking at for your project. Those prices were $1. Okay, a lot of those were single-use processors. You program them to do exactly one thing. The way that you wire them, it does that one thing. Okay, it makes it a lot cheaper. It makes it a lot easier to create, manufacture, just spit out. A lot of these single-use processors are also faster. Okay, they do what you need them to do very quickly. If you have a clocking speed of 1.2 gigahertz plugged into one of these cheap processors, quite frankly, it can do just about anything extremely fast. Now there are also drawbacks, of course, to this system. Drawbacks to this system is that they're not reconfigurable. It does what it does, and you do not change its functionality. Okay, like if you look at an example, any of the toys that talk. Okay, talking toys. You push a button, it talks. Okay. You want to push a button on that toy and change its functionality, you can't. You can't go in there and reprogram it. It runs predetermined audio files, and that's what its job is. Takes an input, predetermined audio file. Has no idea how to handle whether or not the system is doing it right or properly, because quite frankly, it doesn't have the capability of inputting goodness. Its programming capabilities are very limited. Which means if you wanted it to do a more powerful program, it might require multiple processors feeding input to each other. Processor. This processor is involved in processing signal information that's the output of this processor to see what's going on, to be able to measure whether or not it's doing it properly. It's not always something that you can do here. And there are ways to hardwire those, but I mean, the processor itself is very limited. It's part of why it's so cheap. It can't do as much. It takes more processors to do the same thing. This does not handle adjustment at all. Okay, this isn't something where it's like, all right, now push a button, go into the user interface, change up the functionality. No, it doesn't do that. You may be able to turn a dial, which is just a piezo resistor, which is really dumb, which can affect the performance of these. Just turning a dial or flipping a switch. All of those things change the voltage levels that are provided to these. But at the end of the day, if you need something more than turning a dial or flipping a switch, this is probably not going to be your best option. You're probably looking at something more like this, where you actually need to program it, click a mouse, all of those things. So there are some drawbacks. This is a far more optimized version of this, but this is also takes a lot of time and effort to put one of these together correctly. Okay, this, if you given a GPP, you can prototype something relatively quickly. You sit down, just bam, knock it out. With this, it takes a lot of time to standardize the process, to make sure the program is running perfectly, to do quality assurance, to make sure that given the different input conditions, if it's going to be out in the weather or if it's going to be something that gets exposed to the cold, that it's going to be able to perform what it is supposed to do in a timely manner. So this is hard. This is probably your easiest one, just because it uses information that you can understand. But there is one that goes in the middle between these two. And the one that goes in the middle is the single purpose processor. Or the application specific IP. I don't remember what the I stands for. Instruction set processor. Okay. Now this is kind of a hybrid between the two. Okay. The goal here is you want it to have some adjustability, but you don't want it to be something where you're going on this and like in Tesla's user interface, the designers at Tesla made it so that you could actually play like Doom or Minecraft on the center console of your car. That is not this. That is a GPP at that point, because it's something that is reprogrammable. Now that said, it's a GPP that does interface with ASIPs, which is different, or maybe even SPPs, but no, SUPs. But it's something that there's a whole lot of infinitely reconfigurable pieces to that, and it becomes a general purpose processor for the Tesla console. Now, okay, so this is a hybrid GPP, SUP. This is often adjustable. Okay, it may come with a user interface that allows you to pick different features, allows you to change functionality, allows you to actually select different functions that are run, select performance styles, that sort of thing. However, it's built for one application. Okay, I mentioned before, you don't have a Raspberry Pi that is specifically intended to be used to power a motor. You don't have that. You don't have a Raspberry Pi that is specifically constructed such that it only handles video processing. But you can do that with an SPP. Okay, you can handle the video processing, and you can go into the user interface and say, I only want these types of video processing to be done. I want this method. I want these calculations. You can adjust that. You can adjust the way it's done, but it has one purpose, and this purpose is to do exactly what you tell it to, but it's to do this one function. you're not able to go into an ASIP chip and suddenly decide, hey, I'm going to use this to run Minecraft. You can't really do that because it does have a lot of hardwired connections. And really, it's the hardwired connections that make it, like I said, some pins on your processor are forced high and low, much like that truth table that you dealt with for your project last week. They're forced high and low because it's anticipated to do a certain function. And a lot of that hardwired nature is what allows this, blurry, is what allows this to function in the format that it does rather than being a GPP. Okay, now there are some benefits to this. Okay, this has the highest configurability per lowest power. Okay, it has the ability, some of the processors, if you got into some of they're a little bit higher end processors, but some of them you could actually program themselves. You could go in, modify them as you wish. You can change these as needed. Sometimes you can even reprogram them. That's not always all that common, but they are configurable. They do have hardwired connections that force them to do specific applications, or they're connected to certain output components, such that their outputs information has to go through certain processes. But it does still give you the configurability oftentimes because it has some kind of a user interface. It has some kind of a way that you can push buttons or do dials and have it do a different function or have it perform a different processing capability. So it does have the highest configuration per lowest power because it's that hybrid between amazing functionality of GPP and amazing performance of the SUP. These systems do tend to be fairly robust, and they can be designed to be fairly robust. Whereas in the GPP, they do kind of fail a lot, just how they're made. These do tend to be more robust than GPPs. Probably not as robust as an SUP, but they do tend to be very robust. And a lot of processors are moving towards more of an ASIP style. You still are going to have electronic toys that are the SUP, single use. You do them once, they do this, and that's how they're designed. You do have a lot of, you're always going to have SUPs, and quite frankly, you're always going to have GPPs too. GPPs allow people to do things, to prototype, to come up with methods, to do problem solving, to do testing. But this has been a growing market because it is like, if you go look at your car's computer that's in it, is an ASIP. There are configurations you can change. There are things that you can do to modify its performance. There are ways that you can adjust it. But at the end of the day, your car's computer usually doesn't fail, even though it's out there in negative 20-degree weather. It's not usually your car's computer that's failing. It's fairly robust. It can handle that. Now, your Raspberry Pi cannot. Your Raspberry Pi probably wouldn't be able to turn on in that kind of temperature, but an ASIP chip can. Okay. Okay, in today's smart world where we have a lot of intelligent controls of systems, ASIP is becoming much more prevalent because we're finding more uses for a configurable or reconfigurable system that isn't just hardwired to do exactly one thing. Okay, ironically, a lot of IoT devices are single-use processors because you want them to have that their maximum power consumption efficiency and that maximum speed efficiency too when needed. So this is probably not as useful for a sensor for an IoT device, but it does have place in vehicles. It has place in a lot of smart like building control systems are built as ASIP processors. Door locks oftentimes are built as ASIP processors. Is they can input a different chip. They can be updated. Those types of things. So some of the drawbacks, like I said, if this is intended to drive a motor, if that is the purpose of this processor, to drive a motor, this isn't going to be able to do vision processing. It would require a secondary chip that does vision processing, and it would require communication between the two. So, it's not as generic as GPP and not as optimized as the single-use processor. Okay, and that's really the biggest drawback there. It's not that it can't be reprogrammed. It's not that it isn't optimized. It's just that it sits in the middle. It's that happy medium. ASIPs, again, it sometimes takes a lot more intelligence on the front end to figure out what you want it to do, looking at the circuitry diagrams and putting something together. That can sometimes take a lot more robust foresight. But okay, that's all I have for you today. I just wanted to talk about the three types of processors. You do have homework assignments due tonight. I believe it's a reading assignment and a project assignment. I'm going to go ahead and give you your assignment for next week for your project. Is you need to decide what kind of IoT device you want to design. Okay. Once we have that determination, I mean, we've done a lot of research into what IoT is, different types of devices. This week's assignment is to actually go onto Verizon and look at devices that already exist and potentially identify devices that don't exist on their network. There are a lot of systems that have not yet been put into IoT. And that happens. It's going to take some time to build a lot of these out. And Verizon does have a fairly robust method of verifying what kinds of devices can be used on their network. They don't just let anybody with a cell chip just jump in and be like, hey, I'm going to use your network. They have dedicated broadband specifically for IoT devices. This is something that they have constructed in all of their networks. They've built towards this. A lot of cell companies have to allow for IoT to exist. And now they're continuing to work with industry, work with university partners to try to come up with what devices are viable to use this broadband that they have specifically allocated for IoT devices. So that's kind of where the state of technology is, and it's pretty cool what we're working for. But we're not at the smartest world system yet. IoT is an area of significant advancement. It's an area that we will see continued advancement in our lifetimes. In fact, the state of the art today will be relics probably in 10 years, 20 years. We'll go back and look at this as some of the foundational knowledge. So the fact that we're studying this right now, it's a piece of what we expect the future to be. Again, all of the hardware has already been invested into IoT systems. IoT systems are reducing power consumption. They are making systems more intelligent. I tell you all the time that everything's getting smarter in this world. IoT is a piece of that. And I want you to employ your creativity, or, you know what, just build something that you already know. But I want you to pick that, and you're going to be doing extensive research on it. We're going to be designing some circuits. We're not going to plug in a Raspberry Pi. We're not going to use the GPPs for an IoT sensor. I want you to work on building probably what's going to end up being an SUP, a single-use processor, where it's hardwired connections, does exactly one thing, communicates, done. Okay. But I want you to spend some time looking at this. You could be designing something that's very simply just like a water thermal sensor, something that you would put at the bottom of a lake. It could be an HVAC monitoring system to determine whether or not there's a leak. It could be a number of different things, but we're going to be working on IoT sensors, designing that piece of it. And that's where we're headed in this class. So be ready. And if you have any questions, let me know. On Wednesday, assuming that we have the ability to have in-person classes, do bring your Raspberry Pi, because we have some in-person labs to do. Hopefully I see you Wednesday, but at this point, we have to go speed up global warming. Dang it, cold. All right. I'll catch you on the flip side.